What's up guys, welcome back to Matt's Math Tutorials. Today I'm going to be going over arc length. I know last time I said I would go over arc length and surfaces of revolution, and that's because in this textbook they have it as one lesson, but to be honest I think I can split it up because, between you and me I need ideas for more videos. So arc length, what do I mean by that? Well, let's say you have a line, a straight line, and you want to know the distance or the length of that line. Well, if you have a line, completely horizontal, completely vertical, and we're on a Cartesian plane, right? So let's say we're like that. If you have this line, okay, it's pretty easy. You just take this, and you subtract, right? That minus that. Same thing if you have a vertical line, right? This, subtract, right? Now, if you have a line like this, it's also pretty easy, right? Because you can just do Pythagorean theorem, right? You set the whole, right, triangle up, right? Pretty easy. Now, there's also other stuff that we know how to do, right? Including a circle, because, right, because that's just the circumference, right? Um, but other than that, right, I think there's a, actually, I don't think there is a formula for the circumference, in quotes, of an ellipse. I think I watched a video about how there's no formula for that. But anyways, uh, yeah, that's kind of all we know. If I gave you a parabola, right, if I gave you something like this, I said find this length right here. Like if you were an ant walking along this path, how far would you go? You wouldn't really be able to do it. You could tell me this length right here, and you could maybe approximate the actual curve by doing, maybe like that, and just do a bunch of like Pythagorean theorems, right? But you wouldn't actually be able to do it. What you need is a formula. And so uh, I decided that since the formula itself is actually very easy to use, I'm just gonna derive the formula, show you how you derive it. And so basically, that whole doing this thing over and over again was actually pretty accurate to how the formula works, right? So what you say is we're going to have a bunch of these. Well, let me draw this a bit bigger actually, because it's very pixelated the way it's working out there. Okay, good enough, right? So basically, you have a bunch of these little kind of Pythagorean theorem looking things, right? Because you want, you know, this right here, but it's not actually a straight line. It kind of looks like one, but really it's curved. And the smaller you make these things, the less that curve matters, right? So you're kind of going to have a bunch of these things. And of course, eventually you want these to be infinitely small, which means the curve is going to matter infinitely less, right? They're going to be more and more like straight lines. And if you have a thing like that and you're making infinitely small, that's usually a good sign you're going to be doing some sort of integration. Um, but let's look at what this is right here, right? Just this, the first one. Um, we want this length right here, which is going to be, if this is A and this is B, A squared plus B squared is going to be the square root of that. It's going to be this, right? Now, A is, we can call delta x because that's changing x, right? Because x is going from this to this, whatever those numbers have to be. And then B is, of course, by the same logic, change in y, right? So you can say that this right here is change in x squared plus change in y squared. All right, but we want to do a bunch of these. So we're going to do, because we want to do this one plus this one plus this one plus this one. So we're going to do the sum notation with the sigma, if you remember that. So we're going to say this is the sum, right? S for sum. And remember the whole I thing, you kind of need a counter. We're going to say I equals 1, and then we're going to go up to n. And remember, n is the thing we're kind of going to take to infinity at some point. And of course, we have the delta x, that's just an a, delta x squared plus delta y, nope, uh, uh, plus delta y squared. And then we're going to put a little I on these just to show that these are not going to be the exact same delta x and delta y. Well, the delta x is probably going to be the same. Doesn't have to, but I think it will. But the delta y is going to be different each time, and that's going to depend on what this I is, right? Because for each I, you're going to move, however much along the x-axis. Basically, that's what's going to happen. So now we have this whole setup. So what we can do is actually factor out an a delta x, right? So we have this I equals 1, and so we're gonna factor out a delta x from, or delta x squared from these. So if we have delta x squared, if we factor out a delta x squared from this, that just leaves us with 1, and then plus factor out from there. Well, it doesn't really have a delta x squared, so we kind of just have to divide to cancel it out, right? So what we're going to do is delta y squared over delta x squared. Okay. And now what we can do is basically you can kind of split the square root into over the delta x squared and then over the 1 plus blah blah blah. So if you do that, of course, the square cancels out the square root. So really, you're just gonna have the sum I equals 1. I probably don't have to write this every time, but you know how it is. The square root 1 plus delta y squared over delta x squared, and then times, kind of by itself, remember this cancels out with this, so it'll just be delta x. Now this should look very familiar, right? You have a sum, because we're already kind of thinking integrals from the fact that we have to make these infinitely small at some point. And also, of course, when you first learn integrals, you kind of learn about it in terms of a sum. And we now have this delta x, and of course we know with integral looking things, you're always going to have a dx at the end, which is basically delta x, right? So at this point, we kind of just have to convert this into a integral. So the way we do that is by basically saying delta x is closer to 0, right? Or the delta, right? So the way they write it here, right? So the way they write it is, well, let me see if I want to follow this exactly. I see. So something they do. So let me get this out of the way. We have a delta y squared over delta x squared. I'm going to ignore the squared part for a second. I'm going to just say delta y over delta x. What is that? So that's b over a. So that is, if you think about it, in a way, it's rise over run. So that's, you can think of delta y over delta x as the slope. And another thing for slope is, of course, the derivative at that spot. So if we call this whole curve, right, y of x, or actually, no, not that, f of x, then delta y over delta x equals the slope, the value of the derivative of f at x. So you can actually kind of replace this with the derivative squared. So what we're going to say is sum I equals 1 and 1 plus f prime of x squared and then delta x. And then you can go through, of course, the whole, limit as delta x goes to 0, whatever, all that stuff. But I'm honestly, I'm kind of just going to skip to the end here and basically say that once you have this, well, I'll show it. Yeah, so you have s equals the limit. Now they write this kind of in a weird way. So the change, yeah, so they have as kind of the delta approaches 0 of the sum I equals 1 and then of course the 1 plus f x squared delta x. Oh, delta x. Okay. Well, I guess there's technically, oh, also they write this as c, which I think actually does matter. This x right here. I think that does matter because it's not like the x. It's like a very specific value of x, I guess. But yeah, and then delta x. And then you can go to, right, because a bunch of sums where the limit or where the change is getting closer to 0, that's basically an integral, right? So a b, and then root 1 plus, I do it how they do it, f of x, f prime by the way, squared, and then dx. So this is the formula for this, for the, well, I guess it's the length, right? This is the formula. So, like I said, once you have this, it's actually pretty easy to use. Um, you literally just use it exactly how you think you would. So you just find the derivative, and then of course square it, and then go a to b, exactly how you'd use any other integral. So that's why I want to kind of just focus on where this comes from. And it really just comes from basically the fact that you're doing a bunch of infinitely small Pythagorean theorems, um, using the slope, right? The slope comes out of there. So I think that's all I want to do for this video. Um, yeah, well, I guess I could, so let's say this is, you know, x squared plus 1 or something, you know, if f of x is x squared plus 1, uh, f prime of x is 2x, and then you would just do from wherever you wanted to wherever you wanted of root 1 plus 2x squared, so that would be 4x squared dx. And then, throw that into a calculator or whatever you want to do. So that'll do it for this video. Next time, we are going to do the, I guess we'll do the surfaces of revolution thing. To be honest, I don't really remember doing that though, so maybe look for something that I feel a bit more confident on. Although, like I said, I do need video ideas, so I guess, beggars can't be choosers. Wait, what? Basic integration rules. Why do you do that after learning about integration? How does it go applications of integration into basic integration rules? That doesn't even make sense. I think we might have skipped around these quite a bit, to be honest. Yeah, we're not going to do surface. Are we going to do surface of revolution? Nah. Basic integral rules. What does that mean? Let's see, 518. So, let's see. Oh, this is kind of just like, I guess it's just a review. Well, that's what these videos are. You know what? I'm going to torture myself for next week. Oh, that'll be after school starts too. Oh, well, whatever. Integration by parts. Might as well just tackle it. Gonna have to do it at some point. So that'll be next week, and that'll obviously be a big deal. So, all right. That'll be it for this week, and thank you for watching.